Howdy.
Hello, hello. Good to see you again.
Good to see you too. So, what's the update for the week?
Well, we have been running BetaNet for 3 weeks now, 4 weeks. I lose count. I remember that at the 2 weeks mark, we counted the number of blocks, and we were expecting around 2,000 based on what the block time ought to be, and we came out at around 1,000. Excuse me, 2,000. So exactly where we should have been. So that was a really impact. What's the word?
Cool.
Enheartening, cool result where the thing that you designed turns out to work as you designed it. It's nice when that happens, particularly considering that the big elephant in the room, the big question mark, is how does the difficulty adjustment algorithm adapt to composing, which is stateful, as opposed to guessing, which is stateless. And it turns out that it works exactly like we expected it would. So that's nice. We did notice a bunch of network level failures, a couple of deadlocks. For those who don't know, a deadlock is where you have an application that you've implemented using multiple threads that operate independently, and the threads need the same resource at the same time, or they need complementary resources, and they acquire locks on them in opposite orders. And so thread A is waiting for thread B to release its lock, but before B can do that, it needs thread A to release its lock, and they're both waiting for the other to complete their task before they can complete it. Um, yeah, and so we had a couple of childhood diseases on the networking level in BetaNet to eliminate there. And there are a few protocol level upgrades that we've been implementing. One of which is time locking the Coinbase, and another one of which is um, negative fees, which is how you can publish a transaction, broadcast a transaction that still requires some proving work before it can be accepted into a block. And using a negative fee is how the prover can do proof as a service and accept your transaction and include it into something of his creation with a proper proof.
Okay. Is that new?
Um, of sorts, yeah. Up until recently, we thought we were going to have only positive amounts ever, everywhere. Um, and so we did have to refactor the amount structure to allow negative amounts. Um, and also a couple of pieces of logic that were either assuming or checking that amounts could not be negative.
Hmm. Okay. Cool. So things are rolling ahead nicely.
Things are rolling ahead, yes, and it's good that the end of the tunnel is in sight. After so we've done the time locking of the Coinbase. We're in the middle of the negative fees, and after that is done, there's one piece of consensus logic that needs to be updated, which is to require isochronous mining paths, because if you study the requirements to produce a block, some paths are faster than other paths. And so rational miners will always choose the faster path. Unfortunately, the faster path implies that you're not including transactions that were broadcast by other nodes. And so we want to make sure that miners have no incentive to choose that particular path, and the way we're going to ensure that that incentive is absent is by requiring that it takes as much time as the alternative path, which involves
Mm-hmm.
including some transaction from somewhere. And so we haven't started on that yet, but that's the last key piece that's remaining before we have all the features we want for mainnet launch.
Okay, awesome.
There's also some security reviews that are remaining, but we don't expect new features to come from security reviews.
Mm-hmm. Okay. Speaking of security, there was some buzz in the crypto world following the news published by Google that they have a new quantum chip with some new results. I did not dig into it deeply. I believe it's called Willow, but I did see the same question pop up: Is crypto fucked? And I thought you could be the right person to address that question.
I'm the right person to address parts of that question. I'm not the right person to address other parts of that question. So I do have a background in post-quantum cryptography, and I am obviously working in the sense of crypto, meaning cryptocurrencies in that domain, and I can shed light on those domains. What I cannot shed light on is the progress or the state of the art in terms of constructing quantum computers. If you want insights into that, you'd have to talk to someone, an applied physicist who is working for one of those labs. That said, I can speculate on that field, and so from my point of view, there is meaningful scientific progress that Google is achieving. But the thing that turns me off about this announcement is that they are using a meaningless benchmark that seems designed to capture headlines without having substance to back it up. And I would be much more happy if they had stuck to communicating their actual legit scientific breakthroughs
But
instead of this benchmark.
be
We can
that
do
as
this useless task in 5 minutes instead of 500 million trillion years.
be that as it may, you were once able to explain to me basically what is the sort of important benchmark and how does that relate to what they reported?
So the benchmark that they did is basically sampling a random circuit and finding a solution to it. And that's it's designed to make quantum computers look good because quantum computers are good at that. But the reason why it's a useless benchmark is because the task is useless. If you want an apples to apples comparison, you should find an equally useless task and find out how quickly classical computers can solve that. Turns out classical computers are also very good at solving useless tasks. Um,
Aren't we all?
aren't we all? Yeah, even humans are good at solving useless tasks. Uh, the it also indicates, by the way, that they don't have logical qubits. Because if they did have logical qubits, then they could start implementing actual quantum algorithms. And once they can start implementing actual quantum algorithms, then we get benchmarks, usable benchmarks that have an apples to apples comparison that allow you to compare the advantage of quantum computers compared to classical computers.
So
Like
let's hang on.
fact,
Stop. Let's break this down a bit further because many people will not know what a qubit is. Um, so maybe start there.
so a qubit is the quantum analog of a bit. It is the carrier of information. Maybe it's not the quantum analog of a bit, but rather the quantum analog of a flip flop, which is the collection of transistors in the configuration when it stores a bit. Um, and so the interesting thing about qubits is that in order to describe the state of n qubits, you need 2 to the n classical, 2 to the n complex numbers. In contrast to completely describing the state of n flip flops, you just need n Boolean values. And so the state grows exponentially, but the trade off is when you read the state, you still only get n bits of information. And so you have to apply these complex transformations on this huge state and then extract only a very tiny sliver of information. So quantum algorithms are good, or quantum computers are good for problems that require a lot of computation, which you can do effectively in this huge state space, but where the result of the computation is small. So big data, forget it, but deep machine learning, perhaps, classification, perhaps, and a type of the class of problems that fits that description, where the computational load is heavy, but the problem output is small. That's exactly cryptography. We want our problems to be hard and our keys to be short.
Okay, and so the basic building block that's necessary is this qubit, which you're saying they've not yet achieved.
There are many kinds of qubits, and what you need in order to implement general purpose qubits are logical qubits, which are at this point theoretical. They have zero noise. And the way we know that Google has not achieved logical qubits yet is because they are using this ridiculous benchmark that doesn't mean anything. That said, their legitimate breakthrough is that they have error correction. That's below a certain threshold where you start bootstrapping on yourself. And I didn't read into the details of this, but it sounds to me like they achieve this error correction not indirectly through implementing an error correction algorithm, but rather more directly by using error correcting features of physics. So that's the legit breakthrough as far as I can tell. But then I'm not a physicist, so take my perspective with a grain of salt.
So error correction is an important piece of the puzzle, getting to that logical qubit, which then
Yes,
would.
absolutely. So qubits are everywhere, but the problem is that they are noisy. They are very easily disturbed by noise, and so you can't really use noisy qubits for quantum algorithms because your very large state space is destroyed as soon as there is some noise. And so one of the ways to build, probably the way to build a quantum computer, is to find a way to simulate noise-free qubits, logical qubits, using physical qubits. And so this is the reason why headlines of the form, we have 10,000 billion qubits, are absolutely meaningless, because the number of physical qubits doesn't matter. The number of logical qubits matters, and they hardly ever count those. One way to count them is to say we've been able to factor a number of X many bits. If you can factor a number of 10 bits, then we know you have 23 qubits at least.
Okay. And how does this relate to the question? Because sort of the headline that everyone knows is that the quantum computer could break a lot of the cryptography that sort of modern society currently relies on, including some blockchains. And this is something you've thought deeply about at Neptune. So give us your thoughts there.
Absolutely. So, firstly, it's incorrect to present quantum computers as breaking all of cryptography. Anything that relies on symmetric keys or anything that doesn't rely on keys at all, they're basically unaffected. Yeah, you do have a slight speed up due to Grover's attack, but Grover's attack is sequential, and you only reduce the key size by half if you look at the same amount of work, and so it's not a huge threat for symmetric or unkeyed cryptography. The big threat is when you're talking about public key cryptography. This is RSA. This is anything that relies on elliptic curves. Well, not anything if that thing that relies on elliptic curves is isogenies, but anything non-isogeny that still relies on elliptic curves is broken by quantum computers. Um, and scaling to a bigger key doesn't really make sense there. And in terms of the internet and banking, yeah, the internet will take a hit because every time you connect to a site that has SSL enabled, you're exchanging a certificate which is either RSA based or elliptic curve based, and so the quantum attacker could be.
Basically, what happens is that all this public key cryptography relies on a puzzle to be solved that through brute force. So that's if you don't know the key, you just need to try every combination. Is so difficult that it's just not feasible to do with classical computers. It would just take too long, and that assumption disappears because quantum computers are able to just compute so much more, like faster or more powerfully, or how would you phrase that?
I wouldn't use the word brute force. The
Hmm.
best performing classical algorithms are still very sophisticated, but they're still very, very, very time consuming.
Okay.
Quantum computers, quantum algorithms for the same problems are also sophisticated, and they just allow things that are impossible on quantum computers. So I'd say it's a new algorithm,
Okay.
and any classical algorithm you can translate to a quantum algorithm, but not the other way around. Some
Okay.
algorithms can only be implemented on quantum computers.
But so the cracking process would be quicker, orders of magnitude quicker.
Orders of magnitude quicker, yes. But it only applies to a small set of problems that happen to be very useful for generating public key crypto systems.
Yeah.
Um, there are way more classes of problems that can be used in cryptography, and some of them can even be used for public key cryptography, even though we project that they can withstand attacks on quantum computers.
And so we talked about this before, I think maybe in one of the first episodes. And one of the things that surprised me then was the realization that sure, like the network as a whole can see this coming, see the advent of the quantum computer coming, and then upgrade the protocol. But all sort of the old addresses are stuck with the old encryption. So everyone would need to, I guess, transfer their. I'm just speaking in terms of Bitcoin, for instance, they would need to transfer their funds from their old addresses to a new, more secure address.
Well, that's assuming that they still possess the keys and that they're still alive.
Yeah,
Um,
yeah. I'm assuming that. Yeah,
right? In Bitcoin, it is true that a lot of Bitcoins are tied to not the public keys, but the hashes of the public keys. And quantum computers don't do well against hashes. And so, as long as the Bitcoins remain locked under that hash function, they're probably fine. The problem is only when they try to spend those Bitcoins.
hmm,
Because in order to spend it, you have to provide the public key that hashes to that hash digest, and that's when the quantum computer can deploy his attack. And then there are plenty of bitcoins. Satoshi's entire hoard of bitcoins is attached to public keys that we know that are not hashed, and the quantum computer can start attacking those right away. And yeah, so I think it's reasonable to expect the quantum attacker to sell bitcoins to reward the investors into that lab that created quantum computers. Because if they don't monetize their attack, they know that the runner-up in this race will. Um, so in the event of a large-scale quantum computers, the price of Bitcoin is up in the air. And if the price of Bitcoin is up in the air, then so is the profitability of miners
yeah,
because they measure their profits in bitcoins and through block subsidies and fees. And in the end, they need to pay their bills, and they convert their bitcoins to fiat money. And if they can't get enough fiat money, they are going to close down their operation.
And so we talked about this, and so that could send a shock through the crypto world. And what about Ethereum addresses?
Ethereum is, in this particular respect, is worse. Um, all addresses they're not hashed at all. As soon as you have ever received a transaction on Ethereum, your public key is known.
Hmm. Okay, so yeah, so that could cause some shocks, and so Neptune's put some thought into this because you guys are running on post quantum cryptography. So talk about that a little bit.
Well, I mentioned that uh, hash functions and anything that's unkeyed is pretty safe in the context of quantum computers, and that's why we rely on hash functions. The only cryptographic assumption that we're making is that the tip5 hash function is secure. And on top of this hash function, you can build an entire ecosystem of cryptographic protocols, including succinct and zero knowledge, interactive or even non interactive proof systems, Starks, as we have them. And you can use those Starks to construct signature schemes if you're into that sort of thing. You can use them for many other things too. The only thing you cannot do with hash functions is encryption. But then it turns out that we don't really need. Excuse me, the one thing you cannot do with hash functions is public key encryption. You can do symmetric key encryption, and it turns out that we don't really need public key encryption.
Okay, could you expand on that?
Well, the thing we need is a commitment, such that the owner needs to prove somehow knowledge of the secret key in order to
Right.
justify releasing a UTXO and spending it effectively. And the amounts are not encrypted, they are committed to. The big difference is that a commitment can be a lot shorter than a ciphertext. A ciphertext cannot afford to lose information. A commitment can lose information as long as it's difficult to compute a preimage to a commitment.
But does that mean that I mean, sort of behind the hash, you wouldn't even need to run post quantum cryptography, or is that a
The
silly
hash
question?
the hash function is post quantum cryptography.
Ah, gotcha. Okay, interesting. So when we talked about this, I think we said that Neptune was the one of the only blockchains that would be fully quantum resistant. Is that
To my knowledge, I think there may be two other blockchains that I know of that have a similar feature.
okay? Cool. So to sort of summarize, so in the case that let's say this progress continues in an exponential pace, as it sometimes does, and we see a quantum computer in the next, let's say, 5 to 10 years, then Neptune's positioned well to sort of to welcome a lot of new people to the network.
Absolutely, we have a ship that's much more likely to sink than anything that relies on elliptic curve discrete logarithm problems. And so everyone who wants to stay afloat, they're probably going to pick the biggest ship that's still floating,
Mhm.
which is going to be us.
Yeah, but then Neptune's more like a metaphor under the water, isn't it? So now you're on
Yeah,
a.
I guess metaphors don't mix. Sometimes they don't mix.
All right. No, I think that's clear, and that's very cool, and it's cool that it's at least this week it became very relevant, and yeah, who knows where we'll be in another 5 years.
Yeah, and maybe even just after the announcements of all the teams that are competing with Google in producing quantum computers, they're going to have similar announcements, and those similar announcements are going to spark similar buzzes and waves of interest in post quantum cryptocurrencies.
Cool. I think we can
Wrap
call
things
it
up.
there. Yeah.
Yeah, sounds good. Take care.
All
Bye
right.
bye.
See you next time.